Half-life is a concept used to describe the rate at which unstable atomic nuclei decay. It is the time required for half of the unstable nuclei in a radioactive sample to undergo decay, transforming into a more stable state. The half-life is a crucial measure because it allows scientists to quantify the stability of a radioactive substance and predict how long it will remain active. The decay of unstable nuclei is measured using two key concepts: activity and half-life. Activity refers to the number of decays occurring per second in a given sample of radioactive material, typically measured in becquerels, BQ. A higher activity indicates that more nuclei are decaying per unit of time, which is often observed in substances with a short half-life. The half-life provides a more standardized measure, as it remains constant for a given isotope regardless of the amount of material present, reflecting the inherent probability of decay for each nucleus. Radioactivity is a fundamentally random process because it is impossible to predict when a specific nucleus will decay. Each nucleus in a sample has an equal probability of decaying at any given moment, but the exact timing of this decay cannot be determined. This randomness stems from the quantum mechanical nature of atomic nuclei, where decay events occur unpredictably and without external triggers. As a result, while we cannot predict the decay of individual nuclei, we can statistically predict how a large number of nuclei will behave over time, which is why the half-life is such a useful concept. Over time, the radioactivity of a source decreases because as nuclei decay, fewer unstable nuclei remain in the sample. With each successive half-life, the number of undecayed nuclei is halved, leading to a proportional decrease in the activity of the source. This means that after one half-life, the activity of the sample is reduced to half its initial value. After two half-lives, it is reduced to a quarter, and so on. This decline continues exponentially, with the radioactivity never reaching zero but becoming negligible after several half-lives. The half-life of a radioactive substance can be measured using a graph that plots the activity of the sample against time. As the sample decays, the graph will show a downward curve, reflecting the exponential decrease in activity. By analyzing this curve, one can determine the half-life by finding the time interval in which the activity drops to half its initial value. This method is effective because it directly visualizes the rate of decay and allows for precise measurement of the half-life, even in cases where the decay is not immediately apparent. The graph provides a clear representation of the decay process, helping scientists understand and predict the behavior of radioactive materials over time.